Hey guys, today we're going to be doing kind of an expansion of yesterday's lesson, where we introduced the gradient vector mainly, and directional derivatives. But before we jump into that, I kind of want to look back at this for a moment, because it's going to be useful in understanding what we're going to be doing with gradient vectors today. So this is the derivation of, or I guess kind of a proof of that the gradient vector is orthogonal to the level surfaces of a surface, or the level curves of a surface. So if we have just, I guess maybe I could start from the beginning and show this. So if we have if we have some kind of surface, okay, and so it's z, but it's a function of x and y, and then if, say, we moved the z to the other side, then we would have 0 equals f of x comma y minus z, and then we'll call this a function, a big F, of x, y, and z, right? And it's 0. It's a constant of some sort. It could be, I don't know. But we have the x, y, and z, and this is going to be important later, but we have x, y, and z on one side of the equation, which we're going to use later. Now, this surface is like a culmination of multiple, basically infinite level curves, right? You have all these level curves that you could illustrate in some way. You could illustrate them with r of t, right? So that all of these r of t, we'll call them x of t, y of t, and then z of t. And then, of course, the tangent vectors of these level curves is just the derivative of this, right? R prime of t. Okay. Now, something interesting happens when so keep in mind this is equal to a constant. So something interesting happens when you take the derivative of this expression with respect to t, because remember we're defining this in terms of t. We could interpret it that way in terms of t, right? Because it's a bunch of level curves that you could parameterize with t. So if you take d dt of f of x, y, z equals d dt of k, you get, you're going to have to do a chain rule, right? So we have f, which is a function of x, y, and z, and then x, y, and z are all functions of t. So we're going to use a chain rule. We have partial f partial x times dx dt plus partial f partial y times dy dt plus partial f partial z times dz dt. And then this equals derivative of k. K is a constant, so it's 0. And what's interesting about this is we can rewrite it as a dot product. So it's going to be the dot product between this. So I'll just write it like this: partial f, partial x, partial f, partial y, partial f, partial z, dot dx dt, dy dt, dz dt, right? Okay, and we could identify this. This we already know. This is the tangent vector. This is r prime of t. I'll write right here, r prime of t. This we've also looked at. This is just the gradient vector. Nope, not okay. That's really ugly. But yeah, so this tells us that if you dot the gradient vector with r prime of t, the tangent vector, you get 0. That means the gradient vector is orthogonal. It's normal to any sort of level surface or level curve you have on that surface, right? Because their dot product is 0. So this kind of property is really useful in what we're going to do today. And what we're going to do today is we're going to be making tangent planes and using them to do linear approximations. So if you remember from Calc 1, right, if you have like a line and then you have this point right here that you want to observe, if you get a tangent line off of him, you could use the equation for this tangent line that's in some form of y equals mx plus b. You could use you could use this equation and approximate the values of points near this line, right? Because if you really zoom in right there, you have something, let's say that's the point you really care about. Yeah, so like for points really nearby, if you plug in this x value, or this x value, you see that the point that the line is going to give you is pretty close to the one on the actual curve, right? But as you go further and further, but as you go further and further away, say we use this line to approximate this point right here, that's not nowhere close to what it is on the actual curve. So this isn't a good approximation, but this is a relatively good approximation. So yeah, except we're gonna do this, but with planes. So that's gonna be something like, I don't know if you have this kind of surface here, it kind of looks like a sphere, and you use this point and you get like a tangent plane. So I don't know, let's attempt to draw a tangent plane. Right? There's its normal vector, which is just the gradient vector. Okay. So yeah, and we could use this to kind of approximate points near this, right? We're plugging in xy points into the plane to get points that are near this point that we used initially. Funnily enough, I actually couldn't find any past exam problems on this, but it's basically the same thing as finding the tangent plane and then just plugging in some points. Okay. Another thing that you should note is that when we were doing directional derivatives, our gradient had two elements. It had partial z, partial x, and then partial z, partial y. This kind of form of the gradient is used because for directional derivatives, it's like we saw in the practice problems, right? They were giving us, oh, we want you to go this way, right? I don't know, 1, 1. And how I think of it in my head is this direction vector they give you acts like a compass. So if we go back to our contour maps, so this is the z-axis pointing right at you. This is the x-axis, and then this is the y-axis. Yeah, and it's like, oh, what is the directional derivative at this point x, y, z? I don't know, say that's the point we're curious about. So say we're here and we're wondering about the what do you call it? The directional derivative in the 1, 1 direction. Well, this is like a compass, kind of. It's like, it's telling you, I don't know, if you go in this direction, how is your height changing? And of course, compasses don't have a third dimension. So we can't say, well, you can use it, but typically for this class, you only need to use these 2 dimensions, and you could treat this direction vector as like a compass of sorts. If you go in this direction, how is the height of the mountain changing? But in this form, we have partial f partial x, partial f partial y, partial f partial z, because we need to use the, we need to give the, what do you call it? The gradient vector some more dimension, because we're in R3, and we got it out of this equation that tells us if we take these derivatives with respect to this bigger function f, where f is a function of x, y, and z, it's just defined that way that we get 3 elements to slip out of the equation. So this is directional derivatives, this is tangent planes and stuff. So that's basically what you need to know. I'm not, me myself, I think out of what I could research online and discover myself, this is just how they happen to slip out of the equations, and it kind of makes sense with this compass approach, in my opinion. But you can use this to do directional derivatives, depending on what direction vectors they give you. But yeah. Okay. So let's see. We're gonna move on to how we get a tangent, or a tangent plane. So, of course, we know that we've just figured out that the gradient vector is perpendicular. So this guy dot r prime of t is 0. This guy is perpendicular to any level surface on, or any level curve on a surface. So we could use him to get tangent planes out of him. That means if we looked at, I think paraboloids are always, this is like an inverted, well, I guess this is kind of like the sphere I drew earlier, but yeah, so if we zoomed in on this point, if we cared about making a tangent plane at that point, we could do this kind of gradient vector and see that, hey, he's orthogonal to the surface at that point. So we could use him as a normal vector and get a plane out of him, right? So it's really that simple. If you remember, if we have a normal vector, and we'll call him A, B, C, those are his elements, then the equation for this guy's plane is just A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. Okay, so if we're just using this guy as our normal vector, the new equation is just going to be partial f partial x times x minus x naught plus partial f partial y times y minus y naught. And then this is kind of a different part, because typically we have z equals function of xy, but now we're treating it as a f of xyz equals f of xy minus z. Typically, no matter your expression, the derivative with respect to x, or with respect to z, so partial f partial z, is just going to be -1, right? Because this whole function of xy goes to 0, derivative of negative z with respect to z is -1. So you have that. That's all it is. Okay, so let's see. I actually made a whole Desmos little demo thing that I would like to show. Just a moment. Let me just... okay. Okay, so this is, or should I make this a little bit smaller? Let's see. Okay. Okay. Yeah, so excuse the fact that this isn't a complete plane. It's just that I parameterized this plane, so it's not a full plane, just so you could see what the graph behind it is. But this is just a paraboloid, right? And then that is the gradient vector. That's the point we're observing, that little red spot. And then this purple plane is the tangent plane. So, I mean, if you want to play around with this, if you move them around, you see that plane moving in accordance with that. So, yeah, and then look at them. It's kind of fun to watch. But if anyone cares about the, oh, he's going away. But yeah, if anyone cares about the, about playing around with this, I could upload, I guess honestly, you could pause right here and figure out. It's nothing crazy. Okay. So yeah, why don't we use this exact example of a paraboloid in the form of just a standard paraboloid, z equals x squared plus y squared, and get a plane for the point 1, 2, 5. Right, a tangent plane. So we know our gradient is going to be 2x, 2y, -1, right? So the gradient evaluated at this point is going to be 2, 4, -1. And then, wait a sec, I'll be right back. So we're back. So yeah, so this is our normal vector at the point we're interested in. So we just apply them to the equation. So we have 2 times x minus x naught, which is 1, plus 4 times y minus y naught, which is 2, and then minus z naught, which is 5. Okay, and then you just distribute, do whatever you need to do. So you get 2x plus 4y minus z equals, see, minus 10 plus 5 is minus 5. So move to the other side, that's positive 5. So to get this to line up with what we have here, we could go ahead and delete this parameterized plane for our purposes. But then, yeah, actually, let me input them real quick. Yeah, so our point is 1, 2, 5. And then our normal vector is going to be at 1, 2, 1, and then 2. And then our plane equation is 2x plus 4y minus z equals 5. Yep. Okay, maybe I changed some of these colors, because why the hell can't I change colors? Oh. Okay. Yeah. So here is the point we care about. Here's the plane we just got. And then here's the values that we plugged in for our gradient. There's the result. Right. So pretty neat. Okay. So yeah, you could also, if we look back, let's see actually. Oh, I'm gonna shorthand this equation real quick. I just like writing the partial signs, so that's why I always do it. But if we write it this way, right? Plus fy and then y minus y naught, and then plus fz, well, I guess you just have minus z naught equals 0. You could kind of use this equation to model change. So this is a really rare exam question. I never got asked this on the exam. There's like some homework questions about it, if I remember correctly, and I actually didn't find a single exam that tested this, but I guess it's good to keep in mind that it exists if you have time to study for it, but likely not going to be on the test. You could use this and say, well, this is just a change in x, and then we call it dx in the formula. This is a change in y, that's just dy. This is a change in z, that's just dz. So fx dx plus fy dy equals dz. And yeah, you could have a weird, tricky example I found that we could run through. It was down here. Where was it? Okay, so it tells you the volume of a cone is this, pi r squared h, and then it tells you if the radius is increased by 1% and h is decreased by 3%, what is the approximate change in volume v? So the first thing you would do is you would take these partials. We'll say we could change the equation to look like this. dv, change in volume, equals, I don't know, I guess we'll do partial v partial r times dr plus partial v partial h times dh. And then this guy, the derivative with respect to r is going to be 2/3 pi rh. Derivative with respect to h is just 1/3 pi r squared. And then, yeah, so you're increasing r by 1%, and then h is decreasing by 3%. So what you do is out of the, okay, so you could sub in, let's sub in real quick, the derivatives we have, 2/3 pi r h dr plus 1/3 pi r squared dh. And if you divide both sides by v, you can get, so if you, by the total volume, you'll see it's actually kind of neat what happens. So you have dv over v. This is going to come out as a decimal, and we just multiply it by 100 to get a percent change. And then this equals 2/3 pi r h over total volume v was 1/3 pi r squared h times dr, right? And then for the h term, we have plus 1/3 pi r squared over 1/3 pi r squared h times dh. And now what's really neat is a lot of things cancel. So pi's cancel, h cancels, one of these r's cancels. Here on this side, the 1/3 cancels, pi's cancel, both the r squareds cancel. So then you could rewrite this as dv over v equals, let's see, that's 6/3, that's 2. 2 times dr over r plus dh over h, because one r is left here and then h is left here. And what's really nice about this is from the original, you know, that if you look at this, this is a percentage version of the of a change in r, right? If you change r out of this much, and this is, so this variable is going to be, if you had an original r, and then you changed r by that much, so you could replace this with this 1%, which is just 0.01. That's like I think you get what I mean. This represents a percentage. You have a little change in r over the original r, and there's a percent change. So if you plug the given values in, you have dv over v equals 2 times 0.01 plus negative 0.03 because it's decreasing. And let's see, you're going to get 0.02 minus 0.01, or minus 0.03, and you're going to get minus 0.01, so 1% decrease in volume, right? That's what that tells us about. So yeah, now let's move on to some practice problems. Okay. This one's basic, just basically plug and chug one. It tells you find the tangent plane. Oh wait, no, it's a little bit different. The second one is the basic one. So this one says, consider the tangent plane to the surface z equals ln of x minus 4y at the point 9, 2, 0. And then it says this tangent plane also contains the point 2, 1, lambda. And we're supposed to find lambda. What's lambda? Okay, so first we just have to find the equation of the tangent plane. So we're going to get the gradient of f, that's going to be our normal vector. Okay, so with respect to x, it's going to be 1 over x minus 4y. Yeah, and then with respect to y, it's going to be x minus 4y times negative 4, so it's that, and then the z is going to be just minus 1, right? So then we plug in the point that we're at, because we don't plug in 2, 1 lambda, because it's saying that the tangent plane to the surface at the point 9, 2, 0 contains 2, 1 lambda. So we got to get the tangent plane at this point. So if we plug in 9, 2, and 0, let's see, 1 over 9 minus 8. Okay, so that's just 1, that's nice. Negative 4, okay, that's could be, again, 9 minus 8, so this is just negative 4, and then negative 1. Those are nice numbers. Okay, so now we plug them in, you're going to get x minus x naught. So x minus 9 minus 4 times y minus y naught. Y naught is 2. And then minus z minus z naught. And z naught is just 0. This equals 0. So you have x minus 9 minus 4y plus 8 minus z equals 0. Okay. Now we have to find lambda, but we have to plug in these points. So 2, 1 lambda. So 2 minus 9 minus 4 times 1, which is just 4, plus 8 minus lambda equals 0. So let's see, 2 minus 9 is negative 7, minus 4 is negative 11, plus 8 is negative 3. So negative 3 minus lambda equals 0. So you could see that lambda is negative 3. Right. Okay, that's option A. I actually haven't done this one. Yeah, sick, that was right. Okay, would have been embarrassing. Okay, yeah, so that's not too bad. It's a little bit different from just find this tangent plane, but it's not that bad of a problem. Okay, this says find the equation of the tangent plane. Yeah, this is just a really basic plug and chug one. Tells you to find the equation of oh, this one's actually a little bit different because it tells you x squared minus y squared plus z squared plus 2 equals 0. And you are supposed to find the equation of the tangent plane at point 1, 2, 1. Now, you're going to have to use implicit differentiation for this. If this equals 0, then this is the function of x, y, z. And remember, a gradient vector for this is just partial f, partial x, partial f, partial y, partial f, partial z. So with respect to x, it's 2x. With respect to y, it's minus 2y. With respect to z, it's 2z. So don't fall into the trap of this being minus 1. Okay, that's pretty simple. Now to get our normal vector, we plug in 1, 2, and 1. So we're going to get 2 minus 4, 2. Okay, and then we plug them in to the formula. So 2 times x minus 1 minus 4 times y minus 2, and then plus 2 times z minus 1. And then we might have to simplify this, because sometimes what they like to do is if a student gets to this point, they'll see, oh, I guess, what is it? X has a coefficient of 2, y has a coefficient of 4, and z has a coefficient of 2, and they'll choose an answer choice based off of that. But sometimes the constants that'll land up here are going to be off, so you have to work through the whole problem. Plus 2z minus 2, then 2x minus 4y plus 2z, yeah, that's minus 2 plus 8, it's minus 2, okay. So minus 2 plus 8 is 6, and then minus another 2 is going to be 4. So move it to the other side, it's going to be minus 4. Now if you factor out a 2, you get an x minus 2y plus z equals negative 2. So that's option E. Yep. Okay. Now this last one is pretty interesting. I say it has to do with quartic surfaces. I don't know if there's another way to solve this, but yeah, so they tell you to consider this surface z equals 3 minus x squared minus y squared plus 4y. And it tells you find the point on the surface at which the tangent plane is horizontal. So at first glance, you think about it, you're like, oh, you have some kind of surface. I don't know. Every time I think of a surface, okay, I don't know. You have some kind of surface, something like that. I don't know. And you want the points at which the tangent plane is horizontal. This kind of approach doesn't quite work, because I think the way I got through this problem, I looked at it for a moment and I thought, that's a paraboloid. If you really analyze it conceptually, you're probably not really going to get anywhere other than for the tangent plane to be horizontal. If that's our gradient vector, yeah, so our gradient vector has to be pointed straight up or straight down, conceptually. But it could also just go sideways, or well, actually no, that wouldn't give you something that's sideways. But anyhow, yeah, you could think of this, that'll give you a horizontal tangent plane, right? But it's best to just look at the equation. This is a paraboloid. This is really obvious paraboloid. You got z equals a constant x squared plus y squared. This could be, you could complete the square here. That's all it is. So if you play around with this a little bit, let's see, you're gonna get minus x squared plus y squared minus 4y. So then you have 3 minus z equals x squared plus, if we complete the square, you're going to have y minus 2 squared. And then let's see, y squared minus 4y plus, so subtract a 4, add 4 to both sides, 7 minus z equals x squared plus y minus 2 squared. So this is, I guess, this is the equation in standard form. And then what you can do is you could figure out, so like a paraboloid, if you think about it, a really basic paraboloid looks something like this. The only place where the tangent plane for this guy could be horizontal is at this tip right here, where like this is basically just where the tangent plane starts, right? Or where the surface starts. It's at this, like, I guess I call it a 0 point. That's the only place it could be perfectly horizontal. So this is, if I didn't overthink it when I did it, I drew this picture out and I thought of, oh, I need to zero everything out. So that told me, oh, z is 7, x is 0, and y is 2. And that's the right answer choice, actually. If you really want, you could also observe that this is like a max or min kind of situation. And so that means the partial derivatives in both the x and y direction are 0. You can treat it like a max or min type situation, a place where the derivative is 0, right? We could also think of this in Calc 1 terms. This is a maximum. The tangent line is horizontal here because the derivative is equal to 0 here. There's no change in slope there. So if you take partial, so the original equation they gave us is this. If you take partial z partial x, and set it equal to 0, then you're going to get minus 2x. So then you get x is 0. If you do partial z partial y, you're going to get, let's see, minus 2y plus 4 equals 0. So then you're going to get minus 2y equals minus 4, so y equals 2, right? Y equals 2. And then you could plug those guys back into the original equation and see where your z lands. And then you're gonna get 7. Z equals 3 minus 4 plus 8. Let's see, 3 minus 4 is -1, plus 8 is 7, right? So yeah, that's how you treat it. You could just treat it as a min or max type situation, and you can get your answer that way as well. Okay, I hope you guys enjoyed today's video. I think this was a particularly fun lesson. Next, what do you call it? Next lesson is going to be on max and min problems, but it's going to be using a second derivative test. So yeah, so maybe this was a bit much of a question, but I think it's pretty good representation of exam style problems. You kind of have to think outside the box a little bit, but but yeah, you're allowed to think of these as traditional derivatives, just in different directions. Okay. See you guys in the next one.